Hi to everyone and welcome to this DFT Incorporated webinar. Okay, right now I'd like to introduce today's presenter, Arie Bregman. Arie is the Vice President and General Manager for DFT Incorporated. He has spent over 35 years in the valve industry with companies such as Nibco, Jamesbury, and Metso. Arie holds a Master's of Science degree in Mechanical Engineering from Worcester Polytechnic Institute and is active in the Valve Manufacturers Association in the United States, serving on the Education and Training and the Technical Committee, and is also a member of the VMA Board of Directors. Arie, welcome to today's event. And with that, I'd like to pass things along to get things started. Arie, go right ahead.
Hello, everyone. Welcome to our webinar on water hammer. My name is Arie Bregman, and I'm Vice President and General Manager of DFT Inc., located in Exton, Pennsylvania. DFT has been making inline silent check valves and severe service control valves for well over 70 years. And during that time, DFT has learned a lot by listening to our customers. Customers like you, learning about the challenges you face in each of the industries that we serve. We continue to improve our valves, helping to solve customer problems and improving the performance and service life of our products. Today we'll be exploring the common problem of water hammer. Before we get started, I would like to note that I will be answering questions at the end of today's overview. I'll also be responding to questions by email as a follow-up to any questions that we don't get to at the end of today's presentation. We will also post a recording of this webinar for future viewing. So with that said, let's get started with today's topic. While water hammer is a common problem, it is often only briefly touched upon in engineering schools. As a result, we have found that some engineers do not take the cause, much less the effect of water hammer, into account when designing industrial or residential piping systems. Even engineers who do consider water hammer often do not realize the extent of the damage that can be caused in the piping systems by the effects of water hammer. At DFT, our support teams are frequently called in to do a course correction after the consequences of water hammer have already occurred. To help you avoid water hammer and the expenses associated with the downtime, I'd like to explain what it is and how to prevent it. What was that sound? Well, many of you recognize the sound because you've heard it coming from the pipes. It could be in your home or it could be at your company's plant. It's the sound of water hammer, sometimes called hydraulic shock or surge. This phenomenon can occur with any type of a liquid. And while it may look and sound harmless, water hammer places a dangerous amount of pressure on pipes and piping systems and should be dealt with immediately to prevent the costly damage that would result, as well as the repair costs that will be associated with that. It's more than just an annoyance. It's something that really has to be dealt with quite seriously. Water hammer is a hydraulic shock event that can occur in any piping system carrying a liquid. Let's explore this a little further. When a valve is open, the pipe will have a solid column of water flowing through it. That water has inertia, and if you think back to your high school science classes, you may recall that Newton's law of inertia states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and same direction unless it's acted upon by an unbalanced force. So basically, we're dealing with the momentum of the liquid in this hydraulic shock event. So you have water flowing through a piping system, and now it's time to stop that flow. So you abruptly close a valve, or maybe you shut down a pump, but either way, you're stopping the flow. The water will continue trying to travel in the same direction it was traveling in. But now with the supply shut off, the energy stored in the water's motion will cause the liquid to stretch elastically. At some point, the liquid will snap back to its original volume, creating shock waves in the liquid. This resulting pressure wave travels back down the pipe at the speed of sound in that liquid. In the case of water, that can be up to 4,868 feet per second. Just by comparison, the speed of sound in air is 1,126 feet per second. So the magnitude of these pressure waves can be 3 to 10 times the working pressure of the media in the piping system, or maybe even more. So let's see what water hammer looks like in a common application. In this slide, we're looking at the illustration of water hammer caused by the slamming of a swing check valve during the shutdown of a pump. During the pump startup, the initial flow begins and the check valve will open, and maximum flow is achieved. When the pump is shut down during the maximum flow situation, the swing check valve will allow some reverse flow prior to its closing, but then it slams shut. This reverse flow will be aided by gravity, pulling down on the disc and actually pulling any liquid down on any vertical pipe runs. The slamming of the valve creates the pressure shock wave in the liquid due to the momentum of the liquid bouncing off of the closed valve. To better visualize this, think of driving a car. Your body moves at the same speed as the car. If you slam on the brakes, the car will stop moving, but your body, however, will continue to be in motion, moving forward as a result of the abrupt stop. If your seat belt were made of an elastic material, you would stretch that belt somewhat before the belt then slams you back into the seat of the car. This kind of gives you a feel for what's going on with the fluid in the piping system. Many industries are impacted by water hammer. Commercial establishments are often impacted by water hammer, and we've seen that happen in hospitals, high-rise office buildings, residential homes, in fact, and airports. We've also seen the effects of water hammer in a lot of other industries: petrochemical, chemical plants, mining operations, water, wastewater treatment plants, power plants, even refineries. I mean, the list is virtually endless. In building maintenance, water hammer occurs oftentimes with the abrupt shutdown of the flow of water, for instance, a pump shutting down. I mentioned that earlier, but it's quite common. In mining applications, water hammer often occurs when water is being pumped up and out of a mine in a vertical direction, and once the pump stops, gravity pulls the water back down the vertical pipe runs. When this column of descending water slams into an obstacle like a closed valve, a shock wave will occur in the liquid, and that's the water hammer event. In pulp mills, in the process of making pulp, the pulp is cooked in batches. At the end of a batch, the hot pulp exits the cooking vessel. It encounters pockets of liquid, sometimes water left behind from the previous cook. This water then flashes into steam when the very hot pulp comes into contact with it, again creating shock waves in the liquid pulp that's in the pipeline. Cooling towers, it's quite common for pumps to cycle on and off on a very frequent basis. If the water that is being pumped is allowed to reverse its flow, it will eventually encounter a closed valve or some other obstacle somewhere in the piping system. Again, when this happens, the slamming of that water into that closed valve or obstacle sets up the water shock wave that we've been talking about. And just to complete the list, fire protection, refining, sewerage, water supply systems, food and beverage, pharmaceuticals, all have situations in which a water hammer is quite a common occurrence. So now we're going to take a look and see what happens during water hammer. The next slide, we're going to look at a live video of a system that illustrates what can happen during a water hammer event. So looking at this video clip, you want to actually look pretty closely at the pressure gauge that's kind of bottom center of the video itself. And as you'll see during the video, water hammer will cause a massive pressure spike that will jump to 3 to 10 times the system's working pressure. Right now, we're just under 20 psi. As you can see, the pressure spike reaches almost 60 psi, and that's a direct result of the water hammer. You also see some water flying out of some fitting or valve packing in the background behind the gauge. We're going to come back to that video a little later on in the webinar, and you're going to see the after effect of changing the double door check valves to a DFT style axial flow or silent check valve. But because the water hammer pressure spikes can easily exceed 3 to 10 times the working pressure of the system, a great deal of stress and damage can result. Components can fail. You'll have added expenses for downtime. Some of the things that will be common effects of water hammer could be deformed valves or even ruptured valve bodies. Valve discs can be bent, broken, or otherwise rendered inoperable. Gasketed joints or expansion joints can fail, quite possibly catastrophically. Pipe walls can crack, welded joints could leak. You have deformed or shortened lifespan of a lot of the piping systems. You can see weakened or broken pipe supports and hangers as well as a possible outcome of water hammer. In the most extreme cases, water hammer can result in the rupturing of an entire piping system, endangering plant employees. In August of 2009, water hammer-induced effects knocked out Russia's largest hydroelectric power facility, releasing 40 tons of oil 50 miles into the Yenisei River and killed 75 people. During the evening that preceded this accident, the facility experienced large, rapid load swings. The second unit in the plant experienced the largest of these swings, vibrating at 4 times the maximum limit. As the control system decreased the output, the vibrations only increased. This severe water hammer led to the rupture of a conduit leading to the turbine, which flooded both the engine and turbine room, causing a transformer to explode. When left unchecked, water hammer can have dangerous effects. So what can you do to prevent this? Well, first, determine the magnitude of the potential spikes, and then determine how to avoid them or reduce their impact. So first, let's explore how to estimate the potential magnitude of these pressure spikes. There are some equations that we can use to help us in this task that I'm going to overview and review with you in the next couple of slides. And this review, by the way, is not meant to be comprehensive, as there are a lot of technical details that need a lot of understanding. However, there are several textbooks available on the subject of fluid transients. There are also computer simulation programs available to help you automate the task. But computer programs and textbooks always need a little bit of explanation and understanding. That's what I'm hoping to convey in this webinar. So now we're going to get into the math of the matter here. And we're looking at an application of Newton's second law, which is the momentum equation for liquids. We're calculating a quantity called F sub m, which is the momentum force of the liquid in the piping system. And that momentum force is equal to the quotient of rho, or the fluid density, divided by g, the acceleration due to gravity. And we then take that quotient and multiply that times the rate of flow. That sum is finally multiplied by the difference, or the change in velocity, v1 minus v2. When we calculate that, of course, we're looking, as I mentioned earlier, a momentum force. That's going to be expressed, if we keep all our units in order, to be expressed in a unit of weight, like pounds or maybe kilograms, if you're doing it in the metric units. One thing to keep in mind, too, is that we want to make sure that we're always, since we're using rates, either for the acceleration of gravity or rates of flow, velocity, that those are all in units per second as opposed to per minute. It's easy to get the units of time mixed up, so be careful if you're using this equation to try and keep your time units all consistent. What we're looking at here is called the Joukowsky Equation, and was first published by Nikolai Joukowsky in 1904 in a paper that he wrote for the American Waterworks Association, the AWWA. The equation helps us understand the magnitude of the pressure spikes caused by the abrupt changes in liquid velocity. And in this equation, again, staying consistent with my symbols from the previous slide, rho is the liquid density, which is often expressed in pounds per cubic foot. We've got the velocity of sound in water, or A, often expressed in feet per second. I gave you a value of that earlier on in this presentation. That's multiplied by the change in velocity. Again, that could be feet per second type units. And but what we're getting at the end of all this is pounds per square inch. And so if we're using a mixture of PSI and pounds and feet and seconds and all that, we're going to have to throw in a change. And so the gravitational constant, or G, we have to multiply by 144 to convert square inches to square feet. But the product that we get out of that will be expressed as pounds per square inch, or the magnitude of the pressure shock that we're dealing with. So now we need to figure out, what do we mean by the abrupt closure of a valve? And we can determine the minimum valve closure speed from these equations that we're looking at in this slide. And we've got T, which is time. It's usually expressed in seconds. If that T is less than the product of 2L divided by A, which is 2 times the length of the pipe, divided by the acoustic velocity of sound in the liquid of the pipe. Oftentimes that's in feet per second. We'll get a time value, some number of seconds. It could be milliseconds or it could be more than that. So if T is less than 2L over A, we have what's considered a rapid valve closure. And if T is greater than 2L over A, then we have a slow valve closure. We're in the range of a slow valve closure anyways. And paying attention to valve closure time will help reduce water hammer caused by the event of a rapid valve closure. It's one of the 2 scenarios I've mentioned so far, but also requires the understanding of an inherent flow characteristic of the valves in question. Quarter turn valves, for instance, are highly nonlinear, with 80% of the flow being controlled on the last 20% of rotation. So in the case of a quarter turn valve, you need much slower closing speeds than this equation might initially lead you towards, by almost a factor of 4 or 5. So understanding the maximum possible forces that we calculated previously, coupled with the time that we should be programming into our systems to slow down emergency shutoff valves, helps us to understand the type of ways that we can prevent some of the water hammer events that are within our control. So I've touched on some of the causes of water hammer and some of the basic fluid mechanics involved. Let's take a little more in-depth look at the steps that you can take to prevent or mitigate the effects of water hammer. Prevention, of course, is the first and best line of defense. Everyone involved in your facility's operation should be informed of the importance of properly opening and closing manual or actuated valves, as well as eliminating sudden pump shutdowns anytime that can be done. Water hammer arresters can be installed to provide a point of relief for pressure spikes. Stronger pipe support systems should also be used to prevent failure from the shock and vibration associated with water hammer. But another step that is proven very effective is installing silent or non-slam check valves. They can provide a very effective remedy for the shock resulting from the sudden shutdown of pumps. And I'll explain a little bit more about that in just the next couple of slides. So I'm back to that video that we saw very early in this presentation, where we're looking at a swing check valve slamming shut and the pressure spikes that happen over time with that particular type of valve. And as you'll recall, when we watched that video, the pump startup is initiated and initial flow begins. The check valve opens, maximum flow is achieved, and the pump shuts down. And it shuts down during that period of maximum flow through the valve. The swing style check valve slams shut, but only after the flow has reversed. This causes a pressure spike which reverberates through the piping system. Now, with a spring-assisted check valve in place, the valve will close before the reverse flow can occur. And that's unique to this spring-assisted silent check valve. The spring is opposing the flow and will tend to overcome the flow forces as the flow slows down. But the valve will close before reverse flow and does not rely on gravity or reverse flow for the valve to close. So thanks to the spring assist, coupled with the relatively short distance that the disc must travel, by the time the forward velocity of the liquid reaches zero, the valve disc would already have reached the seat and the valve will already have closed and stopped the flow. Reverse flow is eliminated, and therefore the forces necessary to produce water hammer on the upstream and downstream sides of the valve are substantially diminished, if not totally diminished. Here we see the spring and the swing check valves running side by side. Notice the decrease in both PSI and elapsed time of the pressure spikes. Again, this is an illustration to try and help you understand the point of this technology of the inline or silent check valve. So now we're back to that video that we saw, the piping system, with the pressure gauge staring us in the face at about the bottom center of the screen. And again, we're looking at an operating pressure of somewhere around 15 psi. In this video, we've replaced the double door valves with an ALC type axial flow check valve. ALC is a valve that is produced by DFT and has the same face-to-face dimension as the double door valve. With the original double door valve, you'll recall that the system experienced a pressure spike of almost 60 psi, and in the background we saw some water squirting out of either some fitting or valve packing in the background. Our team replaced the double door valve with an ALC valve, and now when the system shuts down, the non-slam check valve being installed, you'll see that there's really no pressure spike at all as the system shuts down and the pump stops. The pressure goes back to 0, then up to 15 psi, but no higher than that. So why does an axial flow check valve work better than a swing check, a tilting disc, or a double door type check valve? It's a very good question, and in the next slide, I'm going to talk about the dynamic characteristic of check valves. So in this graph, we're looking at the dynamic characteristics of check valves. And to make this presentation a little simpler, I'm just looking at a swing check valve, a dual disc valve, and a silent check valve. And this graph has been developed over time by research at a variety of universities around the world, some in the US, some in the Netherlands. But the key to reducing water hammer when a pump suddenly shuts down is the valve closure occurring prior to flow reversal. And in this graph, we're looking at the reverse velocity in feet per second versus the deceleration of the fluid flow. And these characteristic curves will illustrate that in the silent style check valve, if we're operating in the deceleration period of maybe 30-35 feet per second squared, and the reverse flow velocity hasn't occurred yet, we're definitely going to be in the range of non-slam as compared to a swing check, which really has a lot more reverse flow going on before the valve closes. And this is really just illustrating the advantage of the silent check valve over a broad range of other type of valves and over a broad range of flow decelerations. As we saw on the previous slide, a dual door check valve does offer some advantages over a swing style check valve in reducing valve slam. However, an axial flow or silent check valve offers an even higher level of slam reduction. The DFT model ALC is a direct replacement for a dual door style of check valve. ALC valves are extremely easy to maintain, as you can see by the cross-section illustration, and it can be installed in any orientation, either horizontal or vertical lines. The wafer style can fit between mating flanges, meeting the API 594 face-to-face dimension, and can be made of carbon steel, stainless steel, or other materials as required. They can also be customized to customer specifications and fully meet your specific application needs. In addition to the ALC, we do have a full line of spring-assisted axial flow style check valves, which include a model BNC, which is a nozzle-style butt-weld check valve, specifically designed to excel in high-pressure applications for a welded valve installation and buried service. We also have an Excalibur model valve, which is a center-guided inline check valve that provides reliable low-maintenance service, a B1610 face-to-face, and can be actually directly replaced a swing-style check valve because of that same face-to-face dimension. Our model GLC is quite similar. It provides, again, reliable low-maintenance service for a wide range of fluids, fluid pressures, temperatures. It gives us a single-piece body design and is often used in cryogenic applications. The Y caliber is similar to the GLC and providing a low maintenance service for a wide range of fluids, pressures, and temperatures. This model is also welded in line like the BNC, but it has a access through the Y leg that makes it fully inline repairable. So again, it can replace a welded in valve with the inline spring-opposed silent technology. So let's recap. Again, water hammer is simply a hydraulic shock event that occurs in any liquid piping system. The problem is prevalent in a broad range of industries. All those industries will have liquids flowing through pipes, but the water hammer itself can often create a very massive pressure spike that can be as high as 3 to 10 times the system's normal working pressure. These pressure spikes cause a great deal of stress on the piping system, which in turn can lead to costly and dangerous effects to both the facility, equipment, and the employees. The best defense against water hammer is always prevention, and we discussed 4 steps to help you ensure that you are doing your best to prevent water hammer in your facility. You can reduce the magnitude of a possible pressure change through slow valve closure, and so that was the application of Newton's second law to the momentum equation for the liquids. Arresters can be utilized to mitigate the pressure spikes through expansion chambers. We can always train our plant employees and plant operators on how to properly open and close valves to ensure that we don't close valves so quickly that we create water hammer from valve closure. And finally, you may want to utilize spring-assisted silent non-slam check valves wherever it's possible. A number of our products will interchange directly with the valves that you have in your system because of a common face-to-face standard, thus minimizing the cost to reduce water hammer. Well, I hope that you found this webinar helpful. If you're interested in more information about water hammer, we have an ebook available online called Understanding Water Hammer. You simply have to visit our website, which is www.dft-valves.com, and the ebook is located in our literature section of the website. As I also mentioned earlier, we will also share a recorded version of this webinar so you can listen again at your own convenience.
Arie, thanks so much for that great presentation. Okay, now let's move on to those questions. Okay, Arie, here's your first question. What is the technical substantiation of these claims that a silent check valve will reduce water hammer?
Well, the subject of water hammer has been studied quite intensively since the late 19th century. Modern interest in dynamic response of various styles of check valves dates back to around 1980 or so. There are many technical papers that have been written on the subject, some printed by the ASME, others printed in technical papers at hydraulics symposiums. Laboratory experimentation has been done at the Delft Hydraulics Lab in Delft in the Netherlands, also at the Utah State University and Eindhoven Technical University in Eindhoven in the Netherlands, as well as other hydraulic labs around the world. I would hasten to add that a silent check valve may not eliminate 100% of the pressure shock wave, but it will significantly reduce the severity of those pressure spikes. And again, the key is in the spring-opposed disc that's opposing the fluid forces of the flow of the valve. And that spring will close the valve while the flow is still going in the forward direction. And because of that flow the pressure is diminishing, that spring overcomes that force and it closes the valve before reverse flow.
Thanks for that answer, Arie. Here's another question. I've had proposals for equipment costing millions of dollars to mitigate my water hammer problems. Can the solution really be this simple?
Well, as I said a few minutes ago, a silent check valve may not eliminate 100% of the pressure spikes, but it will significantly reduce them. And the best solution may not be an off-the-shelf valve either. There may be some special modifications to an otherwise basic silent check valve that will need to be made. And even a specially engineered valve solution may not cost the millions of dollars that some of the more elaborate pressure surge reduction equipment might cost. So doesn't it make sense to try some simple solutions before making a major capital investment like that? There may also be some advantage to moving the location of a proposed check valve installation. All this can be discussed with our engineers here at DFT to help develop the best overall solution to mitigate your specific problem.
And Arie, thanks again for that answer. Here's another question. What other factors affect or contribute to water hammer?
Well, the closure speed of any and all quarter-turn valves in a system also needs to be addressed along with the shutdown protocols for any and all pumps. Shutting quarter turn valves too quickly in and of itself can cause a water hammer to occur. A sudden pump shutdown is also another big contributing factor, and maybe even one of the more common ones. Finally, vertical runs of pipe coming right off of pumps are also notorious problem areas. And as I mentioned in a previous question, one of the steps of a good solution may be to consider relocating where some of these valves are located, specifically check valves. Sometimes horizontal runs are a better location if they can be accommodated than vertical piping runs.
And once again, Arie, thanks for that answer. Next question up. I hear a banging noise in my steam pipes. Is that water hammer?
Well, no, actually, what you're hearing in steam pipes is called flashing. Flashing occurs when liquid water is heated suddenly by the incoming steam, and that water converts from a liquid to a steam very suddenly. The water expands by a factor of 500 or 600 times its volume in that transition from water to steam. This too will cause severe pressure spikes, and it's the banging that you hear, but it needs to be dealt with in a very different way. The water actually must be removed from the piping system using steam traps or condensate return lines. And actually, this whole subject of steam and valving solutions for steam lines will be the subject of a future webinar that we'll be putting on. So please stay tuned for that to come in the not too distant future.
And thanks again, Arie. We have time for another question. Besides your valves, what are some other possible solutions for water hammer?
Okay, well, this is kind of similar to a previous question. Some of the other solutions for solving water hammer could include air or nitrogen injection. This is done to reduce the sonic velocity in the water or liquid. If you remember back, you can see that the velocity of the sound in that particular medium was a factor in some of the equations. That was that A factor. And if you reduce the sonic velocity, you'll reduce the pressure spikes or the forces that are incurred. This is not always a very viable solution, but it's theoretically possible. Another very popular solution is the use of surge tanks or surge reservoirs. These are used to absorb the shock wave and eliminate the problem itself, kind of like a shock absorber in a automotive suspension. It allows for the absorbing of the shock wave into a big volume of liquid. Again, these solutions can be very expensive, but they are a possible avenue to consider. Another thought besides valving solutions might be variable drive pumps. Variable drive pumps provide a controlled deceleration of the water and liquid, and if you can use them instead of direct drive pumps, you may have the possibility to control the rate of slowdown of the pump and compensate for valves that, for instance, swing type check valves that are relying on the reverse flow to close. You can actually use the pump to slow down the rate and let the check valve, keep up with the flow rate coming out of the pump.
Okay, Arie, we're going to have to wrap things up right there. Arie Bregman, thank you so much for taking some time to be here with all of us today. Again, thanks for taking the time to attend this webinar event. Take care and have yourselves a great day.